I think it is time to introduce the next speaker of today, of this session. So he's Alexey Miller from St. Petersburg State University. And he's going to talk about the behavior at infinity of Gordian graphs. So Alexey, is to you.
Okay, thank you. And I will talk about the behavior at infinity of Gordian graphs of some knot transformations, and we'll have to dive into the context a bit. My speech refers to the classical knot theorem, but we are mainly interested not in the knots themselves, but in the transformations of knots and links. A knot and links transformation is any geometric procedure that transforms a given link into some new link, possibly the same. Moreover, transformations in all interesting cases, of course, are not functions. We can obtain maybe infinitely, many distinct links from the same given link by choosing one or another method of applying the procedure. As an example, we present a classic knot transformation called crossing change or X move. It corresponds to the following procedure. In the given link, we find such a tangle as in the figure on the left and replace it with a tangle as in figure on the right, or vice versa. It's clear that this principle can be generalized. We can replace any two tangles that have the same number of distinguished points on the boundary sphere, that is the same number of threads. Transformation that replace an n-thread tangle with an n-thread tangle are called local transformations, local moves, maybe. We can see some classical local moves: X move, a delta move, and so on. H2 move for band surgery, class pass move. This is a well-studied and very natural class of transformations. The main method of working with certain transformations is to study the Gordian graph of this transformation. The Gordian graph on the set of all knots or on the set of all links, this notation, for transformation delta is a graph G delta K or G delta L, correspondingly, whose vertices are knots or links, and two vertices are connected by an edge if one of the corresponding links is obtained from the other by one-time application of delta and vice versa. Of this graph, we consider natural metric such that the distance between two vertices is the number of edges in the shortest path from one vertex to another. The figure shows a small part of the crossing change Gordian graph. The graph, like the graph of most interesting local transformations, has an infinity number of vertices, and each vertex has an infinity valency. I draw this like that, many edges. Approaches to the study of knot transformations can be mostly divided into two types: the study of local and global properties of Gordian graphs. Global properties differ from local ones by being difficult to express outside the terminology of Gordian graphs. We are more interested in the global properties of Gordian graphs, but we give examples of both local and global properties. Sorry. Okay. The classical local properties are related to the study of neighborhoods of vertices in Gordian graphs. We can see on the screen some classical results about unit neighborhoods. For example, Charlemagne theorem says that in the crossing change Gordian graph, any node in the unit neighborhood of the node is prime. Or here's another example. Blair, Campisi, Johnson, Taylor, Tomova theorem said that for any node in the crossing change Gordian graph, the unit neighborhood of this node contains a node with an arbitrarily large bridge number. And another example, I also give some of my results. And for example, for any node in HN Gordian graph, the unit neighborhood of this node contains an infinity family of cablings of this node. And for any node in this Gordian graph, the unit neighborhood of this node contains a two-component Brunel link with zero linking number. Okay, now let's talk about some global properties of Gordian graphs. The classical global question is the question of the hyperbolicity of Gordian graphs. Jabuk-Lee-Moore theorem say that the the Gordian graph, the crossing change Gordian graph, and the HN Gordian graph for n more than 2 are not Gromov hyperbolic. And in addition, global properties include various complex geometric patterns of Gordian graphs. For example, Hayama theorem says that there are no triangles in the delta move Gordian graph. And Hariuchi theorem says that if the length of the shortest path between two vertices in the delta move Gordian graph is exactly 2, then there are an infinity number of paths of length 2 connected these two vertices, infinity number of paths. And Gambaudo Ghys theorem says that there is a quadratic embedding of the individual lattice into the crossing change Gordian graph. And but most of all, we are interested in a global question related to the behavior of Gordian graphs at infinity. And in 2005, Gambaudo and Ghys raised the question of the behavior at infinity of the crossing change Gordian graph. They proposed studying its ends, that is, unbounded connected components of complements of bounded subsets. I investigate the number of ends. I mean, the supremum of the number of unbounded components when bounded sets are removed. Yeah, and you can see a question, and I have answered this question in more general terms, namely by showing that for any rational move or Cn move or Hn move, the number of ends of each connected component of the corresponding Gordian graph is equal to 1. And Marsh took a different approach to describing behavior at infinity. Namely, he proved that for the crossing change Gordian graph, removing any finite set of vertices cannot make this graph disconnected. And with this point of view, I have essentially generalized this result. Namely, I have obtained that let delta be a local move, such that in corresponding Gordian graph, in the corresponding Gordian graph, the unit neighborhood of the unknown is an infinity set. Is very natural. Which natural property, and then if it's true, then removing any finite set of vertices does not change the number of connected components of this graph. Okay, it's all I want to say. Thank you for your attention. I can see some question in chat. Is there any?
We thank the speaker, and maybe you can check the questions. There is by Vasily Manturov.
I see.
Yeah, so I'm asking, what about the group structure? Maybe for some moves, one can study groups where generators correspond to these moves and relations correspond to some basic circuits which return to the initial node. If so, then we would be able to look at nodes as elements of the group, say, starting from the unknown. So we can say this is the unknown, and by using this move A, we go to the trefoil, and here is the node which is called AB, and so on. And if we return to the unknown, we get the unit element of the group. So is anything like that, was anything like that studied?
This is an interesting idea, but I don't know about some studying like this. But it's I don't know about, but it is good. Maybe. I think about some operation of on the set of all local moves, but it is some different I'm sorry.
Okay. Are there more questions to the speaker? So extra questions then directly and privately. Let us thank the speaker once more.